take his thing.
There we go. Good evening, everybody. Thanks for inviting me and for that introduction, Ann. By the way, just when we're all assembling a meeting like this, one of the things that you can do, if you're not familiar with it, is there's a button in the upper right-hand corner that's labeled Gallery View with that tic-tac-toe board. If you click that, the nice thing is, even though my camera's not focused, it looks like, if you click that, you can see more people at once. You don't need to see every nose hair I've got. You know, it's better if you can just see everybody, and then it becomes more of a social event. Okay, let me share my screen and we'll jump in. There we go. So Ann, shake your head. You can see that prism there? Great, thank you so much. So, and again, thank you all for inviting me tonight. I know you've heard some of this in the past. Hopefully I'll fill in some of the gaps from Matt, who's a experienced guy, has been doing this for a long time. So how is it we've managed to discover so much of the universe, you know, when we haven't even left home? Images, we can see 2 dimensions of the universe, and we can get a fleeting glimpse of a depth dimension during eclipses. And let me drag that out of there. And if we wait a while, we can see, by the way, could you see that? Can you see those people's faces on the right side there, Steve? Now the strip of people? You can? Okay, so there's no reason for you all to see yourselves. So if you wait a while, you can see something about time, and these are, you know, variable stars that we use as standard candles. And if we spread the colors out, we get, oh, look, that's Matt's background. So we get this as if 5th dimension. I love the colors. I mean, they're nature's colors. There's no designer in this here on Earth. So it's just beautiful. And where one color transitions to the other, I always sort of have fun trying to find. Like, where does blue become green in here? Is that blue or is that green? You know, anyway. So these spectra reveal our star and other stars barcodes. They're very unique, and they help us learn all sorts of things about the stars. So I'm going to show you some examples of these tonight. I'm not going to read the bullets, because that's not a good thing to do in these presentations. But you'll see examples of the kinds of things that you can do. It's not very hard. Now, as I've given these talks over the years, I realized I had certain key points I wanted to make, and I thought I'd just lay them out here up front. So first of all, maybe you don't want to capture star spectra ever. Maybe you're an armchair astronomer. Maybe you don't do any imaging, doesn't matter. I'm going to talk about what you can do with the telescope if you care to. But I think what you'll see as we go through the examples tonight is a nice foundation to help us understand the things that we read in the magazines. I know that most of us, I know I certainly do, are sort of passive readers. I'll read something and I'll go, oh yeah, so I sort of understand that. But you'll find that once you've done some spectroscopy, whether it's with your own data or other people's, your understanding gets a lot deeper, and you read things a little more actively, and I'll talk about that later. But you might want to capture star spectra if you remember that first image you captured of the moon. Now, for me, it was, you know, like most of us, it was overexposed, it was blurry. It was still the most beautiful image I'd ever seen. I was like showing it off to my wife and friends and colleagues. Everybody was tired of it. But that thrill, of course, fades. And I found by getting into spectroscopy, I rekindled some excitement in the hobby for myself. Maybe you want to do some science. That was one of the reasons I got involved, to contribute or reproduce former scientific discoveries. I know you're probably like me, and certainly my wife, we're risk adverse. By my wife, I say that when I pull that credit card out, I've got to go through my cost containment officer, and vice versa. It's not a one-way thing. But the nice thing about this is it's not something that you need to spend a lot of money on to get started. I think this is the most significant thing in my talk. If you own the data, your relationship to it is really different. It's just the psychology of it all. You end up wanting to know a little bit more about it because it's yours. And Wikipedia is our friend. And of course, once you've read about your own data, you're more likely to remember it. I know these days things go in one ear and out the other for me. Maybe you're tired of driving to a dark sky site. I'm told Jordan Lake is getting a little bit less dark. And what was that? Menok Mountain State Park. That's what you were saying earlier. We were chatting before the meeting. That's a long drive. And some of the things that I'm going to show you tonight, you can do right from your driveway or backyard. I don't have a PhD or an undergraduate degree in science. I think that's one of the obstacles people may feel to getting started. And you don't need it. Tonight I'm going to sound like I know a lot. It's like a broad river that's really shallow. So, and that's okay. There's no quizzes or final exams. You learn what you want to learn. I'm not a great imager, and fortunately, you don't have to be to do this kind of thing. I'm going to show you examples of things captured with, video camera with, 1/10 of a second frames. And I break just about every piece of equipment I buy. I think in Windows, my favorite command is Edit Undo or Control Z. And the nice thing is there's not a big do-it-yourself project you got to do to get started here. If you do outreach, and I know the club does outreach, it could be, the Astronomy Days event, whatever that's going to be this year or past years. And by the way, I want to thank the club for doing that kind of outreach. I don't know if he's here tonight. Is Mark Gibson here, Ann? Did he show up? Okay, he doesn't sound like he's here.
No, he's not here.
Okay, thanks. Sorry to put you on the spot, Ann. I understand he's a
man.
man.
I was trying to pay attention. I was trying to find my mute button.
I hear you. He's a man after my own heart, and it's great that he does the kind of sidewalk astronomy he does. You'll find this, and I'll point out a couple of the screens that can be really effective. And also coaching high school kids. People win science fair awards with some pretty simple stuff. And finally, you want to hang out with the in crowd or the cool crowd. That's not me. But there are thousands and thousands of people doing this now. It's not cutting edge, but it's new enough that it can still be exciting and you can feel good about what you're doing. We're going to talk a little bit of the science here just to get everybody to the same level. I'll move pretty quickly through this. Sir Isaac Newton, of course, learned that you could split white light with a prism into a rainbow. You can also do the same thing by bouncing that light off a DVD or passing it through a piece of glass that's finely grooved, called a diffraction grating. Bunsen invented his Bunsen burner to study the spectra of things he burnt. You can see the little sample there, and then he put the light through a prism and he looked at the results. He was a real pyromaniac. He burned everything he could find. And the cool thing is he created a catalog of those different spectra, which came to serve us really well, as you'll see in the next few minutes. Kirchhoff was a contemporary and colleague of his. We're not going to drill into a lot of Kirchhoff, except one thing on this screen here. There's not going to be a quiz on this, but there are two types of spectra. One is like this. It's got a rainbow in the background going from red to blue, right, in Roy G. Biv order, if you're familiar with that acronym. And there's gaps or absorption features or lines. And then there's this other type, which is an emission spectra with a black background and just lines. The cool thing is that regardless of which one you get, the lines are in the same position. So again, we're not going to talk about why there'd be differences. That's what Kirchhoff talked about, but it has to do with the temperature of the cloud of gas that the light is going through. So, but these are chemical fingerprints. Look at the differences there between different chemicals. The hydrogen, or let's look at the helium here that you might put in a balloon that you blow up or you get at the circus. Or get at a flower store. Notice it doesn't have a line there, but hydrogen does. And in fact, hydrogen is so common in the universe that we've given its lines, its spectral lines, a name, the hydrogen bomber lines, and actually named the specific lines. For example, this one that's in the robin egg blue is called hydrogen beta. And you're going to hear a lot about that in the next few minutes. This is a periodic table of spectra of all things. So there, hydrogen, notice that you can see there's a hydrogen alpha, there's the robin egg blue, hydrogen beta, and gamma. But look, for example, helium is a very different spectrum. That's why we call them fingerprints. So those of you who are just joining, your timing is pretty good. We're just getting started, and we're talking about the fact that spectra are like fingerprints. We don't have to burn things like Bunsen anymore. We've got these gas tubes, and I've actually got an example over here like that if I've got the gas, wherever the gas tube is. Here's a gas tube. You got to put it in the device. So that's helium. So again, it's pretty easy to do. And we actually have, I created this little desktop spectrometer for physics, chemistry, and astronomy classes. We do a lot of work with high schools and universities on that. So we're going to jump around time-wise a little bit. In 1835, this French philosopher, Auguste Comte, said the stars are too far away. But several decades later, all sorts of people were studying spectra. So he was wrong, but of course he didn't have all the facts because we didn't know what was possible back then. We didn't know that spectra were unique fingerprints, you know, and how can somebody be so wrong? He was a French philosopher, so that explains a lot. But so far, everybody I've mentioned have been old white men. So I want to talk a little bit about women who contribute to the field because they haven't gotten nearly enough exposure or opportunity. So Annie Jump Cannon and her computers were prohibited from accessing telescopes because of their gender. So what they were assigned to do was to study the glass plates, the film plates of spectra from the telescopes. And fortunately, they were really good at it. They studied literally hundreds of thousands of spectra, classifying them, very detailed work. And then they took their experience and they created a new way of categorizing stars in terms of star types. It superseded the incorrect way that the old white men had come up with in the last 50 years previous. Priyamvada Nataraja, she's at Yale and she studies hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA in the late 1940s. She got her PhD. And her vision was the Hubble Space Telescope in the background to her there. And she drove it and made it happen, thank goodness. Lisa Quintana studies exoplanets and discovered some exoplanets around an older star, that cooler star right in the Goldilocks region where there could be liquid water, which we think might be required or is required for life. And finally, Jedediah Eisler, she's at Dartmouth. And looking at my notes here, she studies also black holes and gravitational lensing. So this was a relatively new slide for me. I put it together this summer and it was really exciting. It was like falling down a rabbit hole. There were just so many women doing cool work and unheralded. And so we're moving in the right direction. We still have a long way to go. So how do we get these absorption and emission lines? Many of you may be familiar with this. Forgive me, I'll move quickly. The Bohr model of the atom has these, concentric circles where electrons are orbiting. Those are numbered, and sometimes an electron drops down between levels. This one's dropping between level 5 and level 2. And that can emit energy. In this case, it's visible energy. And we see that as a spectrum. Different jumps create different colors. So for example, jumping this one here, jumping from level 4 down to level 2 creates this aquamarine, that hydrogen beta that I mentioned earlier. Well, what if an electron jumps up? Well, in that case, we get one of those absorption spectra with a rainbow in the background and just a gap. We're going to see examples of both of those tonight. Here's the Hubble spectrograph. They're being serviced. It's being serviced by the space shuttle, my teenage grandson says that that's really not a scientific instrument. He insists that it's a refrigerator and that it's filled with beer because when it's nighttime on the space shuttle, they were real party animals. So, they get a lot of night. In 24 hours on the shuttle, they had a lot of nights too. We need not delve into that. Here's Dale Mace's setup, and you can see it can get very complicated. But what I'm going to talk about tonight is what Matt has also discussed with you on occasion, this little star analyzer grating that sells for about $200. You can mount it almost anywhere. Here's an example on the lens cap threads of a DSLR. This is Vega. There's hydrogen alpha there, and the robin egg blue is hydrogen beta and gamma. So notice it doesn't even have any tracking. That makes it more difficult, and this is a relatively small aperture. So this isn't always a good way to get started unless you happen to have a really limited budget. But the reason I show this is because it's not like there's a black box. There's just this grating. That's all that's doing the work. There's lots of ways to mount the grating. Here's it, like on the preceding page, mounted on a DSLR. This here is a little adapter for the threads that we sell to get down from these bigger threads down to the 1.25 inches. But you can use a FITS camera, cooled, uncooled. You can use a DSLR, like I said before, but here's a imaging source camera, and you just often can screw the grating right onto the nose piece. That's what's down here. It doesn't have to be mono. It can be a color camera, and here's a filter wheel. So there's lots of ways to mount these things. Typically, most everybody starts with a grating, but after a while, if somebody gets interested, they can spend 10 times as much for a slit device. These are considerably more difficult to use and understand because now you're guiding and acquiring your target on like a 20 micron slit, 20 millionth of an inch. So you don't have a big field of view. And so very few people start with these. I know Matt showed this image in his show. This is if you're a do-it-yourselfer, you can create your own slit device for about $500, and it performs fairly well. You can piggyback a DSLR on your telescope if that's how you want to go about it. All right, so we've just raced through the history and a little bit of theory and science. Let's look at what we can do. So we take the starlight and put it through a prism. We get that rainbow, and it falls on our sensor, and we've got a spectrum. Here's a great example. Look at this. These are all different stars captured at a different time. Captured, you can see Torsten Hansen's name down here, and he did this with an 8-inch Newtonian and an imaging source video camera. So these are in temperature order. So the hot stars are up here, the cool stars are down here in temperature order. You know, in OB fine G, KM orders, there's O, A, F, and finally K and M. I'm not going to get into a lot of detail here. We have a lot of ground to cover tonight, but I did want to show you just this one or two examples. Notice that band. It's not just a line, it's a band. Well, on these cooler type M stars, the outer shell is cool enough that not only chemical elements like hydrogen and helium, but also molecules can survive without being incinerated by the heat. And this happens to be titanium oxide. And the truth, I have no idea. I don't know anything else about titanium oxide. I didn't care to learn anymore. You might. So the other example I wanted to show you is this region here, going down to 4800 in the robin egg blue area. So notice how much stronger, wider and darker that line is. That's on a type A star. Remember, and you probably don't because I barely do, but this hydrogen beta line, it happens when an electron drops from 4 to 2. These stars up here, these type A stars, if I can find my mouse, those lines are dimmer because a lot of the electrons, the stars are so hot, they just blow past that level 4 up to higher levels or out. And these stars are cooler, so they don't even get some of the electrons up to that level 4. So you can see the differences for whomever just joined. We're just talking about the kind of spectra you can capture on this $200 star analyzer grading with almost any telescope and any camera. Now, my wife always says that I should dress for success. And so I think in terms of matching things, this is probably the best place to do that. You can see there's the hydrogen beta through that aquamarine color there, that robin egg blue. It's a mess. You know, I just apologize. But, you know, here's the deal. I know some of you are going to be able to relate to this. If you're talking about color, if you look like way down in there, there's actually some gray in there. And, you know, my salon, I haven't been able to get a hold of them. They're not picking up their phone, and that gray is a problem. I know some of you playing at home know exactly what I'm talking about. So hopefully things will change. My wife actually begs me not to put this on during these talks. She thinks that you're all laughing at me, and that's fine with me. A laugh, no matter where I get it, is fine. So you see that crosshairs there? Can you see in the robin egg blue? And it's a trick question that there's a little dimming. I mean, maybe you can, but it's hard to see. So suppose I got time on the Hubble spectrograph that we saw a whole bunch of slides ago, the beer refrigerator. And suppose I submitted a paper and I said, we used the spectrograph on the Hubble and we saw a little bit of dimming in the robin egg blue region. You know, it wouldn't get published, would it? So we have to go quantitative. And so we create a graph like this. It's a pretty simple graph. This is intensity here. And so the star is really bright and narrow. So this is really high and narrow. And if you look at the intensity of this region here, right, it's sort of dim and then gets brighter, 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 and then dimmer, dimmer, dimmer. So this is dim, brighter, 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 dimmer, dimmer, dimmer. But here's the cool thing. Look at that dip off the robin egg blue. Now we're doing science. We can measure the full width half maximum of that dip, where it's located, what it looks like tomorrow, what it looks like with a different piece of equipment on a different star. That's science. So how do we get that graph? So my story is I wanted to do some science about 11 years ago. I got a grading. I went outside, just right outside those windows out there here, about 3 miles from Pike Place Market, a landmark I might mention I don't use when I talk to clubs outside the country. Saturday night, midnight, you know, with my C8, I came in, my blue jeans had grass stains on the knees, right? Because it's Vega overhead in August. Next morning, Sunday morning, I tried to create this graph from that qualitative image, and I failed. I quit, actually. I was using some of the shareware that was out there, and it was real. I mean, I'm being really honest here. I mean, it was half in French. It wasn't documented. It was crashing. And it just didn't reach the level of usability that we've all become accustomed to. And so I told my wife, I said, yes.
I want to interrupt real quick.
Sure.
Got a pretty bad thunderstorm coming almost due northeast into Raleigh.
Okay.
If I lose the internet, the entire meeting will crash because I'm the host.
Why don't you make Ann a co-host? Right click
I can't. We only have one license. So
oh no, she can be a co-host, not a host. Just click on her name, hover over, or click more.
I mean, I've tried that and it won't let me.
Really? Okay.
Yeah, the type of license we have, it only allows one.
All right. Well, I will. If
Just let me say, if the meeting crashes,
it's Doug. You can make me a host. I'm actually a Zoom host, so you can actually make me a host.
Oh, okay. Can you make
if the meeting crashes, I'll bring it right back up as soon as I can.
Oh, okay.
I was going to say, switch me over to host because I'm UPS, so you can switch me.
But
you can switch me.
Your internet isn't.
I think you can have as many co-hosts as you want without subscribing.
Actually, my internet is.
I don't know what that is. Let's just go on with the meeting.
Okay.
Just so you know, my internet is hosted, so I mean it's UPS, all of it. It will not go down. I've got fiber and I've got UPS on both on my routers. Everything's UPS. So.
Okay. So have you guys figured that out? Can I ask a question? There's a question actually.
Oh, sure. Yeah, go ahead.
Since we had a break. So with viewer FOVs, how are separate stars or light source differentiated or are they combined?
FOV?
Yeah, capital FOV.
Field of view.
Oh, in the field of view.
Okay. Thank you.
Okay. Great. I'll show that in just a moment. That's a really good question. Thank you.
Oh, okay.
Great. Good timely question. So, like I said, I gave up with the grading. I told my wife, this is a hobby. I'm supposed to be having fun, and I'm not. I'm really frustrated. I put the grading in the drawer, but it kept bugging me because I wanted to do this. So about 2 weeks later, I said, this weekend, Saturday, I'm going to write something, just a piece of code, just to create that graph. And I did. Sunday, I was done. And I had the graph, and now 11 years later and say 15 or 20,000 hours later, the software is almost done. So that's the way it is with software. My wife keeps saying, would you finish the software? I want to have dinner at a decent hour and at the same time every night. And she's right. So it's not that bad anymore. But I wanted to show you the software for just a moment, not to put you to sleep, which I know is a risk I run. But because I think one of the obstacles that we all have, including me, is, oh no, another piece of software to learn. And I want you to see just how easy it is. So I'm going to go like that and bring up the software. So, and Ann, you can see the software screen now. Shake your head, yes? Great, thanks. So thanks for your help, Ann. So here's an image. It could have come from my Fitz camera, DSLR, video frame, whatever. A running video. There's a star, there's a spectrum, there's a gap there and a couple gaps there. So how do we isolate a star? Well, we just bracket it in. In this particular field of view, there aren't any other stars, but we just drag those lines around it. And now we have that intensity graph. So that peak is from the star. And this spectrum, including that dip, is this spectrum, including that dip there. So that's all well and good, but now what? You know, so how do I know what's what in these dips? Well, remember I mentioned that Bunsen burned everything and created a catalog. And we've built that catalog into the software. So welcome, latecomer. We're looking at software for a moment, but we're talking about spectra you can capture with just a simple grading on almost any telescope. Matt's talked about it before. So Bunsen's catalog is in the software. So I can come down here and say, show me on the graph, and see those lines? Show me on the graph where the hydrogen lines would be if the lines were the result of hydrogen on Vega. This is literally my initial spectrum with that webcam. And look at that, we've got 1, 2, 3, at least 4 matches. So what we're doing here is we have actually detected the atmosphere, the outer shell, the gas shell around the star absorbing, because it's hydrogen, in certain unique spots. And if you're doing outreach, you can make it more colorful. And in fact, this is actually a video. I'll start the video playing. The image is jumping around because of seeing. And so the graph is jumping around. And that I even turn on stacking in the software. Watch how quickly it stabilizes. In fact, I wanted to show you one last thing here that's sort of cool. I'm going to zoom in on this feature. Well, that looks pretty clear because we've just been stacking, but it's pretty messy there. Let me start the video. And you can see that feature, it's not even there a lot of the time. There it's good, that's, you know, so it comes and goes. So a lot of us do stacking if we're doing imaging, but it's fun to see how quickly a stack can improve things. I'm going to turn on stacking. It's running at 2 frames per second. This is actually the video I shot that first night. I'll turn on stacking and watch how long it takes, not long, for us to average out that noise. So we're now seeing a nice spectrum with a nice round, more or less rounded dip. So that's
there's a question. Somebody wants to know what the y-axis is,
good question.
Also, what's the x-axis? If we're gonna go through that, just to,
yeah. Well, just spend a moment on that. So what the software is doing is it's summing up each column's intensity. So these are essentially ADU. This is camera intensity units. So the brighter something is here in a column, the brighter a column will be here. So these aren't calibrated units. They can be calibrated, but it's not something many people do. And the x-axis here originally, just since we're getting into it, the x-axis starts out as pixels. So my camera was 6,400 pixels across from side to side. And then through a couple clicks, which I won't show you right here, we convert that to angstroms or wavelength. So we'll talk more about that later on or in the Q&A. Thanks for asking that question. So the last thing I want to show you as we leave the screen is just that you, in your mind's eye, just remember what that looks like, right? This is the spectrum of Vega. We've got lines showing where our hydrogen bomber series is, because I'm going to show you in a few minutes some examples of some real science that were done using data like that. So here's a star party, another way you could use the software. This is in France, it's in Marseille. This is gas tubes they're showing in my software, but then they transitioned into a star spectrum. You probably wouldn't want to do this at a dark sky party, but at a public outreach in an urban area, it's really compelling. Here's a wide field of view that to answer that question that was asked before. This is with a DSLR, and you can see there's stars and there's spectra. There's a gap there, and you can see here's a star with some lumps. Those are emission lines from this Wolf-Rayet A star. So for those of you who just joined, just in 5 seconds, this is a grating that Matt's talked about before, a couple $100. You screw it onto almost any camera in your telescope or just plain DSLR, and you get spectra like this. And we're going to look at some examples. Your timing's pretty good. We've looked at a couple examples already. Let's look at this here. Janet Simpson in the UK sent me this. You know, the nice thing about this in the winter is it's warm, but right now I don't need that warmth. So when Janet sent me this, I have a confession. I couldn't remember what a Wolf-Rayet star was. I mean, I'd read about them, you know, a handful of times over the years. But like I said earlier, unless you really have a relationship with the data or what you're reading, at least for me, things don't stick. So Wikipedia is our friend. Wolf-Rayet stars are massive stars, you know, like 25 times the size of our sun. And they're late stage. They're really hot, very strong stellar winds, and a lot of the outer shell has begun to dissipate. And what we're seeing in the spectrum is carbon. Now, remember, of course, stars burn through the different elements, and part of that fusion process includes carbon. So we're seeing some of those intermediate byproducts that a star creates. With a backyard DSLR and mechanical tracker in just 30 seconds. That's why I say this is the kind of thing that doesn't require the kinds of skills for those images. I don't know if I have an example, those images in the back of magazines that are so gorgeous. And then you look at the fine print and they're they're like, 20 hours of integration time. I'm glad people do that, but I don't have the skill or time to do that, or the dark skies. So let's look at another emission object, the Ring Nebula. That looks a little different, doesn't it? Well, this is an extended object. So unless you have a slit on a $2,000 or $3,000 device, if you're just using a grating, geez, we got a lot of latecomers. I'm glad they're showing up. Unless you have a slit on a spectrometer, an extended object isn't really generally going to look very interesting. This one does, and you can see there's some hydrogen and there's oxygen. That Roman numeral 3 just means that it's ionized. Some of the electrons are gone. They've left. So, but let's look at another emission object that's extended. There's the Orion Nebula. It's certainly an extended object, right? And they're the same emission lines, hydrogen and oxygen. There's that Roman numeral 3. So again, this is why people step up to slit devices for higher resolution and extended objects. Now, the first time I saw M42, in fact, just for a second, remember the first time you saw M42, where you were, maybe what kind of telescope it was, maybe it was your own, maybe it was at a star party. For me, I was at a star party in Denver in the early 90s. Shoemaker-Levy was coming. I didn't know anything, but I knew I wanted to get a telescope. I went out to this urban star party, first quarter. And it's fun when you can remember when you didn't know something. And for me, I walked out onto the observing field, and what I saw, those cannons they use in the circus to shoot people out of? I saw all these cannons. I'm thinking, what? It's like this cognitive dissonance. What are they doing with these cannons? I didn't know any better. They were Dobbs, of course. They were being operated by people like you and me. And they were describing this great scene, and I queued up and I looked through the eyepiece and I was really disappointed. I was let down. It was a smudge. It was mono. There was no color. It was nothing like the images of things I'd seen in magazines. But still, even if you had that same experience, like me, you probably go back and look at M42. Why would that be? Well, one example is that we've gotten better at averted vision, right? Now we know how to look at things with averted vision so we can have a little bit more sensitive eyes. But more importantly, we now understand what we're looking at. This is the birthplace of stars, a stellar nursery. And with that understanding at the eyepiece, the experience gets that much more rich, even if it's no more detailed than it was that first night. I know all have experienced this. And this is one of the reasons that I've liked spectroscopy, is because it's enriched my visual observing also. Here's Torsten Hansen's video spectrum of Uranus and Neptune. And you can see, again, the molecular bands there, and you can see the dips. This is the methane on these planets. I almost said propane. I think I'm thinking about the barbecue my wife and I are going to have in an hour. So, and by the way, well, we'll leave that. We'll get to that in a few minutes. So this is really remarkable that you can do this with a video camera. So, in 1881, Henry Draper of the Draper catalog captured the image of a comet. And he did that for our newcomers with just this little $200 grating on almost any camera, including a standalone DSLR. There's the spectrum he captured. It's beautiful. It's that nice little string of gems there. And there's the intensity plot. Those are the swan bands. This was captured by a guy in India, Vikrant Agnihotri. He's a nuclear power plant engineer in Rajasthan, in the northwest part of the country. He was a newcomer when he took this image. It's an extended object, but it's compact enough that he was able to capture it with just a star analyzer grating and a small refractor and a DSLR. Here's a more timely example, NEOWISE. You can see there the sodium line, which accounts for that yellow in the tail. So now, anybody who uses a C-clamp, that's my kind of do-it-yourselfer. The problem is, if I was to use a C-clamp like that to hold things together, I'd probably be the one that would crank it down too tight, and I'd collapse the enclosure and destroy my camera. Fortunately, Robin Leadbeater put a star analyzer on the nose piece. He's the designer of the star analyzer and an expert and a huge contributor to our community. Here's a single frame from the video he shot. So the meteor or the Perseid moved that far in that frame, which of course would be a smeared track in most imaging. So that's the meteor and that's the spectrum. At this particular moment, there was a bolide or an outburst, and here's the spectrum he captured. So this is a rather esoteric branch of amateur spectroscopy. You got to wait till you capture something. You really can't go very deep or dark because you're using a video camera, but it's doable, whatever floats your boat. So I'm not going to talk a lot about the solar spectrum since we've had a lot of that over the last 2 years and will again in the coming years, except to mention that that yellow line was discovered in the mid 1860s. We had no idea what it was. Bunsen had never found something with that yellow line. And so they named it, well, they thought, let's see, what's the name for helium or the sun? I screwed up that line, didn't I? The sun in Greek is helios, so they named it helium. And now you fast forward about 30 years, we discovered something here on Earth, a gas that had the same yellow line. The amazing thing is we discovered helium and a physical property of it, right? That yellow line on the sun, 90-some million miles away, not even within it in hand first. Now that's science. So you can detect the differences between novae. Some have iron, some don't. Now, again, Doppler shift, just to show you this real briefly, I know many of you are familiar with this, probably have taught it before, maybe better, but it's, again, the sound change, for example, when a train comes through a station with its whistle on, coming towards you, it's high, going away, it's low. And so coming towards you, it's high, and going away from you, it's low. Same thing happens with light. In fact, the same thing happens. You don't need to go to a train station. Just roll down the window in your car or stand by a busy street. When another car goes past you, you'll hear this, right? High, low. So it's the first time I've tried to actually say it with the pitch change. So suppose we were looking for this triplet. I love that word. It's self-defining almost. And instead of finding it where we expected it, when we captured a spectrum, we found it over to the side. We would know that that object is moving away from us because of redshift. Or if we found it over to the left, we'd know that the object was, again, moving towards us because of blue shift. Let's look at an example of this. Supernovae, we're not going to get into a lot of detail, except it's a star that gets very, very bright and explodes. In this particular type of supernova, 2 stars, one dumps its gas on a white dwarf on this smaller one, and when you dump gas on something hot, you get an explosion. These are called type 1A supernovas. So here's one in M101. And there's a supernova. There's a photograph of another type 1A. It just doesn't happen to be this one. And you can see that expanding shell around it. Well, there's the spectrum captured by David Strange in the UK with just an 8-inch SCT and less than 15 minutes worth of integration time stacked. And there's the spectrum. And look at that deep dip. Now, we talk about standing on the shoulders of giants. And the giants have figured out that these type 1A supernova with 2 stars going around each other have a unique signature with that dip. There's other kinds of supernova, like a single star that it collapses, a core collapse, because it gets too big, too heavy. So those have a different signature. Now, there's not going to be a quiz on this screen, but I wanted to show you for type 1A supernova, see that deep dip right around 6,000? You don't see that on these other core collapse supernovae, do you? So the giants have figured out that if you see that deep dip there, it's silicon. And that's how we identify a type 1A supernova. So here's what Matt and I did. We measured that wavelength at 6150 and we recorded it. Then we looked up what ionized silicon would look like if we burn it. Beach sand, suppose. This is what Bunsen would have found. Now, those two numbers are different. Wikipedia's your friend. I didn't know the Doppler shift formula. But there's not a lot of math there. Even I could stumble through it. And when we did that, we calculated the blue shift of the shell of that supernova coming towards us with a backyard telescope. Now, Adam Risch, you may recall, and his team won the Nobel Prize for research they did right before the turn of the century on the accelerating cosmological expansion. And they used type 1A supernovae. Somehow, I think their equipment might have been a little more sophisticated than this. I'm just saying. But bang for your buck, you can't beat this, I don't think. So this is the kind of thing you can do. There are supernovas that are awaiting classification and get posted on a server on a website, and you could go out and detect whether it's a type 1A or a different type. Now, again, supernovae typically, they're not usually in our galaxy, unfortunately. So they're going to be pretty dim. So it's not as easy as you might like with a average telescope in the backyard. What about the spectrum of a black hole? Now, of course, a black hole doesn't emit any light, but the matter going around it, spiraling in from that gravity, gets very hot and bright. And so David Hayworth here in Portland, Oregon, just down the street from us here in Seattle, captured a quasar. There's its spectrum. See those two little dots of light? There they are blown up. And there's the spectrum. Now, this guy, Martin Schmidt, was in his mid-20s in the 1960s. He was a professional astronomer already. And there's a great transcript of an interview with him that's online. It's linked to from my site, and you can ask me, and I'll send you the link too. He stared at this, and he describes his experience of this discovery. And he can't figure out what those bright peaks are. There's some here that we can't see with our eyes, but we can see the evidence of them in the intensity graph. And so he was so frustrated, he said, okay, I'm going to go back to square one. I'm going to just start eliminating things that these lines can't be. Let me look at where the Balmer lines would be. So that's that screen from my software I asked you to keep in your mind's eye with the hydrogen Balmer series, right? Hydrogen alpha, beta, and there's the beta line in the robin egg blue and the other lines, but they don't line up, right? This peak doesn't have a line. This doesn't really have, so he eliminated it being hydrogen Balmer lines, except it was shifted, and he figured this out. That much redshift meant from Doppler shift, this object was moving away from us enormously fast. So using the Hubble constant, we can calculate that speed or the distance of this object. It's 2 billion light years away. So he was scared he was making a mistake because the explanation seemed so simple. So he conferred with colleagues, but he was afraid, as he describes in this interview, that he'd publish this and then people who really knew what they were doing, you idiot. That's not the explanation. It's too far-fetched. Here's the simpler explanation, the Occam's razor explanation. So, but he was right. He published, and the discovery was that something could be 1 billion light years away and still be bright enough for us to see it, which meant it was enormously bright. So, and that light, the thing that amazes me is that light coming that great distance over that great period of time could be still containing information that we can tease out with such simple equipment. Things don't age that well generally. Here's Martin Schmidt a few years ago. Now, I've been justly accused by people that I am, by showing these two photos on the right, that throwing a rock in a glass house. And they're right, at least he has a head of hair. I'm jealous of the guy, actually. Anyway, great discovery. So 2 more examples and then we'll finish up. So far we've been looking at features like these hydrogen Balmer lines in Vega. Now, how wide are those lines on the x-axis? I'm just gonna, just sort of drop a line on both sides of that feature. And it's, let's see, that's what, 20, 40, 60, 80, 100. So these are like 20 wide. So, our resolution is 20, 30, 50. That's the beautiful thing, is we can be just approximate. We don't have to narrow this down. The point here is that if we want to drill in and look at all the detail in that hydrogen alpha feature, we can't do it with a slitless grating. What we need is one of those expensive gratings with the slit. When we do that, one way we use a device like that is we compare 2 spectra like this. So the moon's in blue, and look at the fuchsia. Vega is in a different position, the hydrogen alpha line. So the difference is only 0.67 angstroms. So there's no way we'd be able to see that on this axis, even if we zoomed way in. It's like empty magnification on the moon. You can keep putting in higher and higher mag eyepieces, but eventually you get to the point where it's just empty magnification. Same by zooming in on a low resolution spectra. You really need the slit. So now we've measured the speed with which Vega is moving in reference to us. So I've got one more example. It requires a visual aid. Here it is. I really should practice. I can't do this. I'd destroy my keyboard when it fell. But this is a star that's spinning very rapidly. So this edge is coming towards you. So the light coming off that edge is blue shifted. And the light that's coming off this edge is moving away from you. So that light is redshifted on the same star. Oh, and the light in the middle, because the rotation doesn't really affect its, radial speed, that light isn't shifted at all. So what would that do to one of these peaks over here? Well, it would steal some of the light that's at the peak and move it over here into the blue and red, vice versa, like that. Let's look at an example of that. Last example. Notice the blue here, that's Altair. Notice how broadened it is. A lot of the light that would have been down here has been spread over to the sides. So now we're measuring the rotational broadening. It's amazing that we can do this kind of thing. This also is done with a slit device. So I wanted to show you the differences between just a slitless low resolution grading and some of the higher order things that people do. These are things that amateurs do too. So how do you get started? Just very briefly, you need a grating, you need some sort of camera. You may need some sort of a adapter, and that's because the distance between the grating and the sensor, it's not critical like focusing a telescope, but it can't be too far away or too close. So I've got a calculator on my site, and lots of people just send me their specs. There's a link there to do it. And I figured out, and I show them how I figured it out, whether they need a spacer or two, something like that. And then you need software. Now, my software, I haven't mentioned the name very well. RSpec stands for real-time spectroscopy, because you can do it with video. Here's some of the shareware that's out here that I've tried in the past. It's really powerful software. It's gotten a lot better over the years. It's still a steep learning curve. I hear that from a lot of people. I'm biased, of course, but very, very powerful software. So, when you get these graphs, how do you know what dip is what? Well, there's some really amazing books out there. Just to finish up, this is a cool book. I want to just show you 2 pages from it. So there is a spectrum. Notice they've called out some features in that spectrum. But for a knuckle-dragging programmer like me, that's not really very helpful. Because if I look at this, they're calling out nitrogen and helium. So what? I'm not an astrophysicist. I don't know the significance of that. But what he's done, Richard Walker in this book, is he's got lots of text aimed at us, not professionals, so you can figure out what you're seeing. So it's great those resources are available. Now, my software is free for 30 days. You can download it from the site. The AVSO is jumping in to spectroscopy and has been for many years. Arnie and Stella, both being professionals, appreciate the value of it. And in fact, I gave a talk to, I think it was 300 or 400 AVSO attendees in August. And we're going to do another workshop online, a Zoom workshop. I think it's in November. I hope it is, because I got some prep work to do yet. So, but I gave a workshop about 4 years ago to about 100 AVSO members at the SAS conference, if you've heard of that in LA. And that was recorded. So you tonight or tomorrow morning could download the software, watch this workshop. It's about an hour long, where I walk the audience. They're all on their laptops using sample data, and the sample data is also downloadable. You may not own a telescope or a DSLR or never want to do this. And the software is free, so I'm not urging you to do this so I make money. Well, I am urging you to do it. Well, some of you might end up doing something and buying something from me. But the real thing is, if you do it with your hands, you go through a couple samples, you'll really, in your bones, you'll understand spectroscopy. And then when you're reading a magazine and they show you a spectrum or they talk about redshift, you'll know what it's about. You'll understand it because you will have done it. There's lots of opportunities, not as many as we'd like, for pro-am collaboration. A lot of the names down here are amateurs in our community. More opportunities coming, especially as the AVSO that now has a spectral database. The BAA in the UK has a spectral database. There's a spectral database in France, and you can contribute to all of those. Again, be truthful, the opportunities aren't great. There aren't a lot of them now, but they are growing, and they'll continue to grow. So in the last, say, 50 minutes or so, and 55, as well as the last 200 years, we've come a long way, haven't we? I'd like to thank you all for smiling at some of my jokes and for inviting me tonight and listening patiently. I hope I added to what Matt has presented over the years. I'm happy to answer any questions that you've got. I'll stop screen sharing for a moment. I may come back to it. And I think I showed you this, that if you're seeing just me in the center of your screen, click on the button that looks like this. in the upper right-hand corner. It's a toggle. You can go back and forth. I think this is a more interesting screen so you can see everybody. Thank you all again. Okay, so Michael Keefe asked here about APOs and chromatic aberration. Wonderful question. Chromatic aberration is our enemy because we're splitting the light by color. And so if the focus is different on those, if there's any aberrations, it's going to affect the spectrum. So reflectors, of course, typically don't have that problem, but you need a higher end telescope, with ED glass or something like that. Even some of the telescopes that are supposed to be low chromatic aberration sometimes have trouble. But in general, you're right, Michael, chromatic aberration is a problem. I don't know what page 87 is, Anne, but yes. I
saw the answer. So basically my question was, if if you have a spectrum, I don't know, iron or something like that, and you see that it's shifting to the right, or if it's shifting, and that means that it's going away from you, or maybe that's the opposite, and shifting to the left, it means it's coming towards you or going away from you. But my question is well, there's two questions. So on 87, there's a calculation as to how you can calculate how fast things are going. So that was my first question. And then my second question is, how do you get the middle? Is that from the Bunsen? So he burned out, he burned what iron was, and he has a spectrum of what iron is, but it's standing still. So
right. So you compare the difference. You expect that there'll be a spectrum here, but you're seeing it here, and you go, wow, that difference has to be from Doppler shift. Right. And then you just use that Doppler shift formula to calculate the difference. One of the things you could ask that along these lines is, how do you know whether the star is moving away from you or you're moving away from the star? And there's no easy way to know. I mean, that's all about relativity and frames of reference and things. Cosmological expansion is an interesting thing. When I published my first article on this in 2011 in Sky and Telescope, Bob Noye, who was the editor-in-chief of Sky and Telescope, contacted that guy who won the Nobel Prize, whose name I've already forgotten, and said, Tom is calling this spectral shift Doppler shift on the quasar. Is that Doppler shift? He knew the answer. And this soon-to-be Nobel Prize winner, he won the Nobel Prize a few months later, he said, nah, it's not Doppler shift. And the discrimination is sort of subtle, and it's sort of fun that scientists do this to appreciate their precision in thinking and talk. Doppler shift is when something's moving. And for cosmological expansion of space, he said, nothing's moving. Space is, expanding. It's sort of a subtle point, which I guess I understand. But let's see, Letitia, thank you earlier for your question about the y-axis. I need to say that more clearly, and it was a good question for you to have asked. So thank you for that. And what other questions do people have? You can just turn your mics on and have at me.
Yeah, kind of a follow-up question to what Anne asked about just a second ago.
Go ahead.
Okay, yeah, so I don't know how far away like the characteristic wavelengths are of the different molecules you're looking at, but if you're looking at maybe a blue shifted or a red shifted molecule, is there any like guesswork involved if you're like, do any of them typically overlap and you're not sure if it's a little bit farther away from where you might expect? Is there any guesswork as to if it's a red shifted or blue shifted from different direction? Does that make sense?
That's a good question. I'm not sure of the answer. In general, when you're looking at such enormous redshifts as we're looking at with the quasar, there's really very little question because the distance that thing had moved on the graph was enormous. So typically all the elements are going to be shifted within the Doppler shift formula. Some of them will look like they're shifted a little less than others, but that's just because of the way the formula works. The other question, Zach, that you could ask, it's a little more tricky, and that is, what if there's a lot of different peaks, and how do we know which one is which, or if they're sort of overlapping? And that's the devil's in the details. It can get tricky to do that. And that's where, again, books like this book, as well as there's other books linked to on my site, help us. And I think the biggest help is the online communities that we have now. people upload stuff all the time and go, in fact, somebody uploaded something today and said, it's open season on this image. Have at it. Let me know what I did wrong. So identifying things, especially if it's something new, can be a little bit of a challenge. So that's my answer for that. Other questions?
Thanks.
Sure. Anyone? Bueller?
Yeah. Hi, Tom. It's Doug Lively. I just wanted to kind of expand on Letigia's question. Is that the units that you are actually using on your y-axis? It wasn't really clear. You can see, like, say for instance on slide 100, you've got like 0.25, 125, 0.25, whatever. But then what is that? Is it hertz? What's your actual? What is that? What's the labeling on that? What's the labeling of the unit on that axis?
That label is ADU. And let me find an image to show you. Hold on a second. Boy, that's not where I want to be. Give me just a moment here to find it. It's a good question. If I can find it. There it is. Okay, I'm going to bring it up and then I'm going to share my screen. Share the screen. There. So on the left of my software, suppose we had the orange lines just 4 rows apart. So this is the pixel well value, right? On a video camera, this would go up to 255. On a fixed image camera, it would probably go to 64,000.
Yes.
So what the software does is sums up this column and then uses that value in the same distance on the x-axis, and we get 65. So what are these units? Some people call them analog digital units or arbitrary units. These literally come from the flux of the photons that have been filling the well, but actually getting, erg per square centimeter converted to, electron volts and all that. Not erg, electron volts per unit area. That's really tricky to do. Most people don't do that. Typically, we're just looking at relative intensities on the x-axis. Does that help answer your question?
Yeah, so it's a measure of intensity. Is that what you're saying?
That's what I'm saying. Yeah, exactly. Any other questions? All right, well, listen, I'd like to thank you all very much. I hope that, like I said, this has been enjoyable for you. I'm going to leave you to your fun. You can, after I'm off, you can, throw eggs at me or whatever. And I love the field. I love helping people. It's an accidental business. My passion is what I enjoy doing, and I consider it a privilege, is to help newcomers. I'd like to thank the club for the outreach that you do. And again, I've got my notes here that I made earlier, whether it's Mark doing his stuff or the astronomy days or other things. I think that's us all paying it forward and backward, and it's nourishing. It's nice when we can serve other people, and it's fun. And this is an example of that. So thank you all again. Have a great evening. Anything else, Ann?
Just one last thing. The RSpec-Astro, that is your website. Is that correct?
It is, yeah.
Okay.
And yeah, you can just search RSpec Tom Field and you'll find me.
Okay.
Okay.
And so that was all I had. Thank you very much for
my pleasure.
doing
Great
that.
job, man.
Thanks,
Yeah,
Doug.
great.
And
Thank you.
Steve, you're welcome, Jim and Steve and D. Huns. And Steve, thanks for doing the technical stuff behind the scenes. I appreciate it. And I wish you all health and safety, and that the next year should be a better year than this year. We can only hope. See you all.
Oh, yeah. Thank you.
Thank you.
Yep.